Okay, let's go a little bit deeper into the topic of test benches. In particular, what we are going to do is look at a couple of visualizing aids that are useful in this context. In particular, there is a notion of something called a VCD, or what's called a value change dump, right? VCD outputs are commonly used in order to sort of see the various different kinds of outputs that can be created as part of a system, right? And as an example, we might have, let's say a test bench which is running a counter. I would instantiate the counter DUT, and then what I would do is basically, before giving the stimuli, I would declare something as being the dump file. Okay, as you can see, this starts with the dollar sign. So a dollar dump file is a system function or a system task, which basically says, okay, set up a particular file, give it this name, and dump all the variables corresponding to this test bench into that file. Now it's interesting because what it's effectively saying is, look at every single signal that is present inside the system and dump it into the file. But the question then comes, okay, when should I dump it, right? Should I dump it at every sort of simulation time step, or is there some more selective way in which I can do this? And that's where the idea of a value change dump comes in, right? The idea is similar to a dollar monitor. I look for changes in any of these values and decide, okay, am I supposed to, and do I see a change in the value of clock? Okay, then let me go in there and mark that the value of clock has changed. But interestingly, in a dollar monitor, what would happen is every time clock changed, it would print everything out on the screen. VCD is a bit more clever than that. What it says is, at a particular time instant, if clock changed, only the change in clock is recorded in the file, right? If something else, let's say the count also changed at the same time instant, it will record a change in that count as well. But it does not necessarily record a change in count. Let's say that count remained the same. Let's say that the clock was going from 1 to 0, a falling edge on the clock. Count is unlikely to change at that point. It will just record that there was a change in the clock and nothing on count. So it's a very compact and efficient way of recording changes that happen during a simulation. An example of what we can do with VCDs is, you can, for example, say that I have a counter and I want to dump out everything in the test bench, but don't go inside the DUT and dump out all the values out there. Or I could say dump the values in the test bench and one level of DUTs inside, but if the DUT in turn has internal modules, don't go in and dump their values. Okay. You could also choose to dump out very specific signals like the clock or the reset or the enable and so on. There are many different ways in which we can do this, right? So in order to sort of appreciate this a little better, let's go and directly take an example. So this example that we see over here is a test bench that can be used in order to verify the functionality of a counter. What does it look like? It basically has the registers for the clock, reset and enable, because all of these are things that are going to be driven by the test bench, and then the actual count comes out from the DUT, so that's declared as a wire. Once again, preferable to just use logic everywhere instead. You will also see that there is a module out here that does clock generation, right? We will talk about that in a moment. This is once again a common convention. What we want is, there is a clock, I have an initial block whose only job is to set up a clock. It basically says that right at the beginning of time, set up the clock with a value of 0, and every 5 nanoseconds change the clock to the naught of the previous value. So after 5 nanoseconds, clock will become 1 because it started off as 0. After another 5 nanoseconds, it will become 0 again, and so on, right? The interesting thing is, this looks like it is an infinite loop. Well, it is, right? But the interesting thing is that every 5 nanoseconds, this thing basically stops, changes the value of clock, and then tells the rest of the system, okay, now I'm going to wait until I'm actually told that time has passed, another 5 nanoseconds has passed. So even though there is a forever which very explicitly looks like an infinite loop, right? It turns out that that's precisely what Verilog is very good at modeling. It says, okay, I'm now going to wait over here until time everywhere in my simulation has advanced by 5 time steps, and then I will once again change the value of clock and once more go back to sleep. Okay. The second initial block is the one that actually does the dumping values into the VCD file. It basically sets up a VCD file, it says what values to dump over there. It also does a monitor out here, right? So you can also see what the values are changing. And finally we have a third initial block, right, which actually does setting up the reset, setting up the enable, waiting for some time so that one clock edge has passed, then enable the counting, wait for a little bit of time, disable the counting, enable it again, and so on. Okay. So what happens when we run this is, first things first, we can see that the simulator sort of goes through, compiles it, runs it, and the dollar monitor has basically kicked in over here, and you can see that lots of things got printed out, right? It basically at time 5 it found that clock changed and therefore it triggered the dollar monitor. At time 10, well, clock as well as reset both changed. At clock 15 only clock changed, but it prints out anyway, right? At clock 20 it turns out that enable changed. At clock 25, that's the first positive edge of the clock. How exactly does the counter work internally? I'm going to skip over that because it will become clearer when we talk about sequential logic modeling. So for now, just go with the thing that every 10 nanoseconds, whenever the clock goes from 0 to 1, the counter is going to increase, and that's exactly what the dollar monitor shows you out here. Okay. Now the interesting thing is, okay, we have all of this, but we would like to understand, can we actually see the output in some kind of a more intuitive or graphical format? Okay, and for that what we can do is, so what we can do is to activate that option of run EPWave after completing the simulation, right? And you will see that EPWave is basically a kind of a waveform viewer, right? It has some very nice instructions, or nice operations. It has instructions over here which basically also allows you to how do you sort of move around in EPWave and view the different functionality that we have. Okay, for now I'm just going to give a very high level overview of what it is. The interesting things you can see, for example, are that it has all of these signals, and you can go click anywhere on it and it puts a vertical line which is called a cursor. Now that cursor essentially allows you to sort of see where in the present time. So for example, if I go click here, you can see that it shows that I'm currently at 50 seconds, right? It should be nanoseconds ideally over here, but it has taken the default time unit to be seconds because I did not specify anything else, right? I can go click somewhere else and I'll find that it's 80, I'll find over here that it's 95, and so on. I can see exactly where the enable signal went high. I can also see where exactly the counter value started changing to 1, 2, 3, and so on. Okay, the fact that the reset signal was high for 10 nanoseconds and then became 0 after that. So you can see that this basically is giving you something very similar to a timing diagram, but more interactive. You can actually sort of see that this is directly output from the Verilog code, and you can sort of scan through it and in fact look for particular changes and so on. Now why did all of these values get repeated, right? You have clock over here, you also have clock over here. If you hover over it, you will find that the first one says counter TB/clock, the second one says counter TB/DUT/clock. This relates to the dump vars 0 versus 1. 0 basically says dump every signal in the present level as well as in submodules. So it's basically printed out the clock, count, and so on inside the DUT as well. Okay, we could have avoided that by giving dump vars 1 instead. Also, as opposed to the timing diagrams, you will probably notice that the transitions are very sharp over here. They are basically vertical lines, right? Except for the fact that I have sort of a slight angle over here when I'm having multi-bit values count going from 0 to 1, for example, right? So as I said, the convention of signals changing just after a particular time instant is something that is done in WaveDROM to make it a bit more easy to visualize. Depending on the kind of waveform viewer that you have, it may or may not do something of that sort. Okay. The important point is there are a lot of very nice features that come when you start visualizing like this. I can, for example, go here and sort of go towards the next transition and so on. Okay, so I could well, I can zoom in, I can basically zoom out over here. I can also move the signals around in various ways, or I can look for various kinds of different patterns that get matched over here, right. So these are tools that are generally available to you for examining the outputs generated by a test bench, and can be very useful in terms of debugging whether something is changing the way you expect or not. Okay. So as you can see, when we have this open EPWave after run option selected, that's when it comes up automatically once you have finished the simulation. And you will find that what it did was it basically ran through the entire simulation, called $finish, then it found the VCD file and opened EPWave. Okay, and that's basically what was the reason for bringing up that picture out there. Now the interesting thing about Verilog, and this is really where HDLs become powerful, is the fact that I can write code like this which allows me to generate complex stimuli. What do I mean by a complex stimulus? Let's say that I wanted to write out something which a value, a 4-bit value, taking many different combinations 0 0 0 0 0 0 0 1 and so on, right. It turns out that I can do it very trivially by just running a for loop in my test bench, right. I can basically say assign a equal to I of 3 colon 0, where I is an integer like this, wait for 10 nanoseconds, which would typically be 1 clock cycle, right, and then assign a is equal to the next value of I, right. If you needed to write this out, you would normally write a equal to 0 0 0 0 hash 10, a equal to 0 0 0 1 hash 10, a equal to 0 0 1 0 hash 10 and so on. Not only is that tedious, it is also error prone. This is a much cleaner and neater way of actually doing the entire programmatic way of generating stimuli. That's really where the power of a language like Verilog being used in the context of a test bench comes in. Alright, so Verilog has this notion of tasks and functions. Let's take a brief look at what those correspond to. This is basically just like we would use a function in C in order to modularize code. We basically, if we have something which is going to be repeatedly done, we define a function for that so that we can use it more easily, right. In the same way, we can have something like a task which basically can apply a stimulus. It can take an input, it will assign the value to data and assign the value to a signal like A, wait for a certain amount of time, it can call a $display and so on, right. The interesting thing is I can then have my code looking a lot cleaner. I can basically say apply stimulus of the value 5, apply stimulus with the value of A, and all of this sequence of steps that I have over here gets very neatly done by basically expanding it out almost like a macro statement, right. It allows us to combine repetitive steps and basically define an easy way of doing it. Now this is actually interesting if you think about it, right. There is also a notion of functions in Verilog which is much closer to the notion of a function in a language like C. A function basically does not have a notion of delays inside it. It is just used for certain computations, right. It must return exactly one value, it can only have input arguments, and is typically used if you want to model simple combinational logic, like maybe counting the number of ones that is present inside a particular bit sequence, right. It can be used, for example, in continuous assignments, right. And if we want to use it for operations like maybe calculating checksums, performing simple arithmetic operations, Boolean logic and so on, it's a very nice way of making your code more modular and easy to understand. Tasks in that sense are actually more powerful, right. They actually can include timing constructs like delays. They could have 0 or multiple outputs. They can have input output. They are almost like modules, right. And what it allows you to do is to sort of create a sort of abstraction of a module that can be used to model a complex sequence of steps. So as we will see in the example, it can be used to model complex sequential operations which have multiple steps in them, but they cannot be used in continuous assignments. They can only be used inside procedural blocks, either initial or always blocks, right. Very useful for things like bus protocols, test sequences. The apply stimulus that I already showed is an example of that, and so on, okay. So let's look at a quick example of something like this. here we have a test bench which has a couple of different functions out here. One of them is used for calculating parity. Now what is parity doesn't matter, all it says is it takes an 8-bit data and it does a so-called XOR reduction, right? It's an interesting way of writing the code. All that it says is take all the 8 bits and XOR them together in order to calculate a single bit value at the output. I have another function which is a bit more complicated. It actually takes an 8-bit value. It then runs a for loop through all the 8 bits, and if data of I is equal to 1, it says count is equal to count plus 1, and finally the function count once gets this value equal to count, and that's how it returns a value. There is no return statement as such, but I do have a function, an end function out here. On the other hand, I have tasks. One task is, for example, a send packet. It has an input and an output. It first sets the value of the output to 0, it then waits for 10 nanoseconds, sets the output to 1, performs a $display statement, waits for another 20 nanoseconds, once again makes valid equal to 0. So this is clearly a somewhat complicated sequence of steps that we have, right? There is also something else called process element, which would actually go through and it would use the functions count ones and so on internally, right? And finally I have my overall test stimulus which goes through and just calls send packet, as this almost looks like a function but it's not, it's actually calling a task. Why? Because this send packet would go through multiple steps. It would make valid 0, then 1, then set some value for data and then make valid 0 again and so on, right? So all of those things can happen, and therefore what we can say is I can actually run a for loop which goes through and does a process element. Fairly complicated sequences of operations can be made much more compact and neat by using functions and tasks selectively. You have to be careful about where you use them and how you use them, but the bottom line is if I actually go through and now try to run this entire code, I'll find that there is this for loop out here, the processing of elements, where it actually goes through and runs everything. All of these tasks, all of that gets run as required, and finally it says as each element is being applied to the input, the maximum number of ones that have been seen so far is being computed and printed out here. Okay, so the reason for using tasks or functions, a very important thing to keep in mind, they make sense mostly only in the test benches, right? But they can be very powerful to increase the sort of value of the test bench in the sense that make it easier to use and easier to sort of extend in various ways, right? So sort of judicious use of these kind of things can make your test benches much clearer to understand and also easier to reuse and more modular. Now finally, in the context of test benches, there is this notion of so-called self-checking test benches, right? Basically what we say over here is, let's say I wanted to test the output of an adder, right? What I would do is I would define a task which would apply an input. I would also know what the expected output is in this particular case, right? Now how do I actually get the expected output? That has to be provided by the designer, or it could actually be computed using a function over here, right? And what it says is if sum is not equal to the expected value, right? Notice that it's not actually calling a function to calculate sum. It assumes that since the adder is there, once I have applied the inputs and waited for 1 nanosecond, sum has automatically got updated. So there's no calling the function out here. Sum automatically gets updated because I've applied the input. I check whether the output is equal to the expected output. If not, then I display an error. What this means is that if I actually ran through a test bench of this sort, which would just call checksum 5 and 3 should be equal to 8, checksum f and 1 should be equal to 1, 0, and so on, right? If any of these things did not match, maybe because my internal adder implementation was wrong, it would immediately print an error out here, and I can further add things like, for example, just stop the simulation, right? Or do something else which basically says, hey, don't proceed out here because you immediately need to mark the fact that this thing went wrong, right? all of that can be done very effectively inside the test bench. And this idea of a test bench that automatically checks whether the outputs are the expected outputs is called a self-checking test bench. These things are very useful for automatic verification of results, right? And they are ideal for use in so-called scripted workflows, where we basically write a script which automatically applies certain inputs, checks the outputs, and then proceeds further depending on whether the test bench passed or did not pass, right? In particular, especially if you have had some background in software design, large-scale software design, you might have come across this term called regression testing. And the idea of regression testing is that there is a test case which you just run against the system every time that you make changes in some parts of the system, and if any part of it fails, that test case will automatically fail and will flag that there was a regression, that something that you changed over here caused some previously passing test to fail. These are very valuable and very good ways of sort of making sure that large designs can be built up systematically using smaller and simpler designs. So in general, good practice for organizing a test bench looks something like this, right? You have a top level module and you have something like multiple different tasks within that. You might have a task for clock generation, one for applying stimulus, one for verifying the output, and then finally running various test scenarios, right? Each of these what you probably do is to define these tasks and then order them within your initial block so that they all get applied as required. And there are many different common design patterns that you will come across in test benches, right? Once again, we will be looking at examples of those as part of the practice code that you write. But for the most part, it would look something like this. If I wanted to generate a clock, I could either generate a module by itself and think of a clock literally as a separate chip on my breadboard. What does it do? It initializes a value of clock to 0 and every 5 nanoseconds inverts the value of the clock. This module can just run by itself, but I could equally well have designed it as a task and it could be implemented over there as well. Which one you choose is a matter of convenience or personal preference to some extent, or more likely, depending on the kind of scenario, the team within which you are working, there would be standard conventions that are followed out there. So some quick takeaways as far as these more advanced uses of test benches are concerned. VCD files, value change dump, they enable more detailed waveform analysis. The use of tasks can make stimulus generation modular and reusable, which is a very crucial part of how we write good test benches. Self-checking code can reduce the requirement for manual verification, and in general, organized code structure improves maintainability. Now this is one of the things that you need to keep in mind. What you are trying to do over here is not just learn the syntax of Verilog. You are trying to do digital design, which means that there is a design that needs to get implemented and then needs to be maintained and improved upon as time passes, which means that how well it is written, how well it is documented, and how it is structured can make a big difference to the final design and the maintainability of the design as you move forward.